All right, welcome back, ladies and gentlemen. Today we've got 5.8 analyzed graphs of polynomial functions. And today we actually finally get to graph polynomials. And it's been a long time coming, but we're finally here. On the back side of this handout is where we're going to do more of the analyzing of the graphs. But we're going to start out by graphing. And I've got a sentence here to get us going. By using zeros, end behavior, and the y-intercept, we can draw, or actually let's say we can approximate the graph of a polynomial. By using zeros, end behavior, and the y-intercept, we can approximate the graph of a polynomial. And let's get us started here. We'll do an example. We are going to graph f of x equals parentheses x plus 2 parentheses x minus 1 squared. Now, ladies and gentlemen, is this in factored form or standard form? Well, because it's not multiplied out all the way, we're going to consider this to be factored form. And it turns out factored form is a little bit easier to graph because it's going to be easier to find our zeros. If it's in standard form, we're going to require a little bit of work to get our zeros. But today, we'll be able to get our zeros right away. So let's go ahead and do that. Because these are our factors, our zeros are going to be x equals negative 2 and x equals 1. The long story is we're doing the zero product property. Put a 0 here. The zero product property says you can set this equal to 0, this equal to 0, but it just ends up changing the signs. So we can get negative 2 and 1 as our zeros. But we learned the other day that because of this exponent of 2, that means 1 is going to be a 0 two different times. So that gives it a multiplicity of 2. The negative 2 only shows up once, so we leave it be. Now we learned the other day that depending on if the number of times an answer shows up is odd or even, that will determine if the graph crosses or is tangent at that 0. So since negative 2 only showed up once, it's going to be crossing. It crosses. The 1 has a multiplicity of 2. It shows up twice. It's going to be tangent. The graph's going to be tangent at that 0. Now, I also have described it as the graph's going to bounce at that 0. Well, let's move on to end behavior. End behavior is actually what you're going to start out with when you graph, is you're going to think about end behavior. And again, we did this the other day. To get the end behavior, we need to know the degree, and we need to know the leading coefficient. Well, the degree we can find by counting out how many times x is going to multiply, so we're going to get 2, 3. That's our degree. Our leading coefficient is negative 1. So with an odd degree, are we going to think of a line or a parabola? Well, we learned that an odd degree is like a degree of 1. So we're going to think of a line here, and because it's a negative leading coefficient, we're going to think of a line going down from left to right. So make yourself a little sketch. Down from left to right. From that little sketch, we're going to write our end behavior. As x goes to negative infinity, f of x goes to positive infinity. It's going up. As we go to the right, as x goes to positive infinity, f of x or y is going down to negative infinity. And the last thing, so actually I got to be honest with you, right now you could make a pretty decent approximation of the graph. But to add to our level of detail, make it a little bit more accurate, we're also going to be required to find the y-intercept. And if you recall, the y-intercept is where the graph crosses the y-axis. Well, it just so happens that if you're on the y-axis, what's your x value? What's your x value if you're just hanging out here on the y-axis? Yeah, that's right. Your x value is going to be 0. So we're going to use that to help us solve for the y-intercept. We're going to do f of 0 equals negative 0 plus 2, 0 minus 1 squared. And we're going to evaluate this. Take your time with it. It'll end up being negative. In the parentheses, I'll get 2, negative 1 squared. Now I'm going to do order of operations, continue with order of operations. I'm going to square this. That'll be 1. And then I'm going to multiply everything together, and I'm going to get negative 2. Now that's the y-intercept. You can write it a few different ways. You can write it as y equals negative 2. You could write it as a coordinate 0, negative 2. However you want to do it. Okay, now we're ready to graph. And let's actually start off by plotting our zeros. We've got a negative 2, we've got a 1, we've got our, and we'll move on to our y-intercept there is at negative 2. But when I said that we're going to start with the end behavior when we make our graph, when we actually draw our roller coaster sort of shape, we're going to look at our end behavior to determine if we start up here or down low. And according to our little sketch we made, we're going to be starting up high. Now, these polynomial functions, they tend to be pretty steep, I guess you could say. So I'm not going to start way over here. I'm going to start pretty close to where my first 0 is. Now I'm going to think this through before I start graphing. It's going to be coming down here, and when it hits negative 2, it's going to cross. Now I'm going to have to turn around. I'm going to have to hit this y-intercept, and I'm going to have to go up here and hit 1. Now at 1, it's going to be tangent. So that means it's going to turn around at that 1. Or another way to think about it is it's going to bounce off of that 1. And there we'll have it. So let's do it. Coming down here, crosses, have to turn around. We've got to hit that y-intercept. Doesn't matter, you know, if you go right to it or however, but I think it'll probably go a little bit below it, come back up and hit it. And then we're going to approach this a little bit differently because it's going to bounce off of it and come back down. And that is a pretty solid approximation of the graph. You're welcome to use Desmos, type this in, see what the graph actually looks like to compare. I'm not going to take the time to do that right now because I know these videos, sometimes you want to get through them as quickly as possible. Alright, so I'm pretty excited because we've just graphed our first polynomial function by hand. Now I do want to point out some things that we're going to point out, or that we're going to look at on the back. Notice you've got these places where it changes direction. It's going down, then it goes back up, going up, then it goes back down. Those are called turning points, and we're going to explore those a little bit more on the back of this handout. Alright, so we got our first one down. Let's try another one. Let's graph f of x equals 2 x plus 1, x minus 1, x plus 2 squared. So think of this as 3 steps. I'm going to go ahead and write my zeros out. I'm going to make note of any multiplicity. Because these two only showed up one time apiece, that's odd. So the graph is going to be crossing. It crosses at -1 and 1. Because the multiplicity, because this answer shows up twice, that's even. So it's going to be tangent right there. Tangent. Alright, let's talk about end behavior. To get our end behavior, we're going to think of the degree. 1, 2, 3, 4. We're going to think about the leading coefficient. The leading coefficient is 2. So what shape do we think about when we got an even degree? Well, you're going to think of a parabola. And because it's a positive leading coefficient, you're going to be thinking of a parabola opening up. That's how the end behavior is going to look, is a parabola opening up. So to write that out, we'll say as x approaches negative infinity, going to the left, f of x goes to positive. As x goes to the right, positive, f of x is going up, positive. Let's get our y-intercept. Our y-intercept is where x's value is 0. Whoops. 0. 2 times 0 plus 1, 0 minus 1, 0 plus 2 squared. We'll do order of operations. Simplify those parentheses. And then I'm going to square this, and then I'm going to multiply everything. So I square this, I get 4, negative 4, negative 4, negative 8. Y equals negative 8. Plot our zeros. Plot your y-intercept. And we're going to look at our end behavior to determine how to start this thing out. We're going to start up above, and we're going to come down, and we're going to 2, but at -2, it's tangent, so it's going to bounce. But it's going to be a quick turnaround because it's got to then cross through 1. It's going to go way down there to get that -8, come back up, and cross at 1. Now, if I hadn't have found the y-intercept, I probably would have turned around a little too soon. Does that make sense? So let's go ahead and do this. It's going to come down, and it's going to be tangent at the -2. Quick turnaround, cross. Going to go way down here and come back. Now, I got to be honest with you, my my graph's a little weird. There shouldn't be any of this kind of bending in, out, then in, and stuff like that. Oh man, oh my goodness, that's about the same. Anyway, I won't bother with it. But remember, this is a sketch. It should be real smooth looking. Now, there's some teachers that, and probably in some upper level classes possibly, they'll be really curious about the amplitude, like how far up is that turning point. And what they'll do to make our graphs more accurate is they would have you figure out y's value at between these 2 points. You'd put in -1.5, crunch the numbers, find out where that is. You might find out, well, it actually goes up pretty high there. I don't think that's the case. I think we got it pretty accurate as we go there. But that's one way to make these graphs a little more accurate, is to get values in between your zeros. They can kind of help you out. Well, there you have it. We've graphed a couple of polynomial functions by hand. Oh, excuse me, end of the day, tired. All right, well, flip it over. I got some more information for you. On the back here, we're going to do more analyzing of the graphs. But along with that, I need to get you to thinking about turning points. So let's put a little kind of definition up here. I want you to think of turning points as local minimums and maximums. So what I mean by that is, if you're at this turning point where it changes direction, if you're standing in there, you're going to look around and think, wow, I'm in the lowest spot there is. Well, the only reason you think that it's the lowest spot there is because you can't see that there's this other lower spot. Okay, so this is what we call a local minimum. If you climb the hill here, you're at a local maximum. This graph actually goes to higher points, doesn't it? But standing right here, you're feeling pretty tall in that vicinity. So we call it local minimum, local maximum. This down here is a local minimum, but it turns out it's also an absolute minimum because this graph does not go below that point right there. So if we're talking about domain and range, that would be important for describing our range, and maybe we should talk about that. But anyway, we'll talk about that more later. So turning points are local mins and maximums. There's an interesting relationship between the number of turning points and the degree. Now I'm going to go ahead and write it out, the relationship, and we'll converse about it a little bit, see if it makes sense. I'm going to switch to red here. The graph of every polynomial function of degree n has at most n minus 1 turning points. There's this interesting relationship between degree and turning points. The biggest thing I'd like you to come away from is this insight right here, that your degree is always more than your turning points. Okay? Over time, you'll get the more nuanced the more nuanced relationship between the two. The fact that it's at most n minus 1 turning points. Let me give you an example to maybe help you out a little bit. If you happen to have a 5th degree polynomial, well, you would have at most how many turning points? Well, at most you would have 4 turning points. So that's the most you could have. So what that means is we're thinking of like an inequality. You're going to have 4 or less turning points. It's pretty common, at least in my experience graphing polynomials, oftentimes you'll have a 4th degree polynomial, and when you graph it, it just looks like a parabola. There's only 1 turning point, okay? That's why we say the number of turning points is 1 less or less, okay? So it's 4 or less. Now we're also going to be responsible for looking at it the other way, the flip side. So if you had 27 turning points, now I know that's a little bit excessive, but you know, it's possible. If you have 27 turning points, well, remember the degrees are more than your turning points, so you would have 28 or more turning points. 28 or more turning points. Oh, I'm sorry. Sorry, I misspoke. I daydreamed for a second there. No, I misspoke. 28 or more degree. If you have 27 turning points, the number of your degree is going to be more. So you say 28, and it could actually be or more degrees. 28 or more. Now, for these two graphs that are given, by the way, these are kind of weird graphs. I was just doing the best I could with the technology. But you're going to be asked to answer, basically to analyze these graphs. Take a look at a graph, describe the turning points, describe the zeros, describe the y-intercept, and also to describe the possible degree. Okay, also describe the possible degree. So let me write out what the instructions would be here. Okay, for both of these graphs, you're going to number the turning points. And estimate their coordinates. That's the first thing you're going to do. You're also going to estimate the zeros. Now, if you recall, zeros are also x-intercepts. Okay, so you're going to look at where the graph crosses the x-axis. You estimate the zeros and the y-intercept. And finally, based off of the number of your turning points, you're going to determine the least degree of the polynomial. The least degree of the polynomial. Remember, the degree is more than the turning points, okay? So since they're asking for the least degree of the polynomial, you're just going to go one more than the turning points, and that's your answer. So let's try this out. I would like for you to try to be accurate. Try to be accurate. It's an estimate. Try to be accurate to the nearest tenth. So for our first example, number our turning points. Typically I go from left to right. We got one right there. Another. 3 turning points. Estimate their coordinates. Turning point 1 appears to be at -4 and up, I don't know, 1.1. 1 and a little bit more, right? Turning point 2 appears to be at, I'm going to say, -1.2. And it's up not quite to 5, so I'll say 4.8. And turning point 3 appears to be past 3 a little bit. We'll say, I don't know, 3.1 for the x value, and the y value looks smack dab at -5. So we numbered the turning points and we estimated their coordinates. Next up is we're going to estimate the zeros. And the zeros are going to be x values where the graph crosses the x-axis. It appears to cross at 1, and it appears to cross at 5. Alright, so that's first part of the question. Next, our y-intercept appears to be at 3. You can write y equals 3. You could write 0, 3. You could write y-intercept equals 3. I'm kind of indifferent. And then finally, class, with 3 turning points, what's the least degree that you could have for this polynomial? 4 is the answer. 4th degree. All right, and we've done a little bit of analyzing. What I would encourage you to do is try out this next one for yourself. Try that out, and then do some homework. Practice a little bit. Page 390, 3 through 10, 15 through 20. You'll need a little bit of graph paper. Let me give you some warnings on the assignment. Sometimes the y-intercept is large or small, depending, but it goes off your graph. So if you happen to have a y-intercept that's off the graph, just kind of put a little dot up there and then say like 122 and just make sure your graph hits it. But that's how I deal with it. I don't recommend changing the interval of your graph. Our book is fond of changing the interval on just the y-axis and not the x-axis, and that kind of distorts your graph a little bit. I mean, so does doing what I just suggested, but I like it better. It's easier to deal with. Well, thanks for watching. Have a great day.